Hello everyone, this is Dr. Zach, and today we are going to define and use infinite series. Last class we worked with sequences, and we know that sequences are a list of terms. We might have A1, A2, A3. So these are your terms, and they will go on as far as you need them to. However, a series is the sum of the terms, and an infinite series means that you would have an infinite sum. What we're interested in is finding out what the sum of that infinite series might be. And in order to do that, we're going to consider the sequence of partial sums. So the sequence of a sum would be S1, which is only the first term, S2, which would be the sum of the first two terms, S3, the sum of the first three terms, and of course, Sn, which is the sum of the first n terms. If we can find the sequence of partial sums, Sn, and if that sequence converges to S, then we know that the series, which is your infinite sum, will also converge to S. And S is called the sum of your series. It will be written as S equals the sum from n equals 1 to infinity of a sub n. If S of n diverges, then your series will also diverge. So our goal is to determine whether an infinite series will converge or diverge. In order to do that, we're going to look at the partial sums. Let's write out a few terms. So our sequence of sums, S1 is going to be equal to 1/2. S2 is going to be 1/2 plus 1 over 2 squared, and that is 3/4. S3 is going to be 1/2 plus 1 over 2 squared. That, remember, was 3/4, and we're going to add 1 over 2 to the third, which is going to equal 7 over 8. S4 is going to be the sum of the first four terms, so that'll be S7 over 8 plus our 1 over 2 to the fourth, which equals 15 over 16. Now at this point, hopefully you've recognized a nice pattern, because we're really interested in Sn. So when you take a look at your numerator and compare it to your denominator, did you notice that it is 1 smaller? So we could rewrite the numerator as 2 to the n minus 1 divided by 2 to the n. Or we could have 1 minus 1 over 2 to the n. Next, we're going to find the limit of Sn, because if the limit of Sn has a solution as n goes to infinity, then our infinite series will have a solution. And you can see that as n goes to infinity, S of n is heading to 1, which tells us that the sum k equals 1 to infinity, 1 over 2 to the k, is going to be equal to 1, because it converges. For example 2, we want to know if this problem will converge or diverge. So again, let's write out a few of the terms. So write out your terms. We have 1 over 1 times 2. We have 1 over 2 times 3. 1 over 3 times 4. 1 over 4 times 5. Now let's look at our partial sums. When we set it up, notice that the first partial sum is 1/2. The second partial sum is 2/3, 3/4 for the third, and then 4/5 for the fourth. What I'm hoping that you notice is that the 4 and the 4 match, so S of n is going to be n divided by 1 that's larger, so n plus 1. So there's our S of n. Next, let's see if S of n converges. If we have the limit as n goes to infinity of n over n plus 1, that answer is 1. So that means that our infinite series, k equals 1 to infinity, 1 over k times k plus 1, must be equal to 1. There is a second way to consider the problem. Did you notice that our original series is a rational that could be written as a difference using partial fractions? Now, I want to explore what happens with this. If we substitute 1, we will have 1 minus 1/2 for the first term, so that's for term 1. Then if we substitute in 2, we have 1/2 minus 1/3, so that's term 2. If we continue with this process, we'll have 1/3 minus 1/4. Well, that would be term 3, and then it would go on and on and on until the last term. There is no last term, but we could write 1 over n minus 1 over n plus 1 to consider what happens near the end. Did you notice that the 1/2 cancel out? The 1/3 cancel out. So we're going to keep the first term and the last term because that 1 over n is going to cancel out. So we could actually rewrite this problem and figure out the limit as n goes to infinity, 1 minus 1 over n plus 1, which is equal to 1. So this is a different way to do the problem, and it's called a telescoping series. So if it's telescoping, that means that some of your middle terms will cancel out because of the subtraction sign, and you need to figure out which terms remain as you go towards infinity. By the way, just to be clear, this series does converge, and it converges to the number 1. Let's check out example 3. So if we were to write this out so that we can recognize our terms, we have -1 plus 1 minus 1 plus 1 minus 1, and that goes on and on until we get to infinity. So if we look at our partial sums, S1 is going to be -1. S2 is going to be equal to 0. S3 again is -1, and S4 is 0. So Sn has 2 different possibilities. The series will add up to -1, and that only happens for n is odd, or it's going to be 0 for n is even. Now, if we take the limit as n goes to infinity of S of n, that answer does not exist because it's bouncing from -1 to 0. Therefore, this series will diverge because the limit has to exist for that partial sum. Next, let's look at k. The series is k. If we write out our terms, we have 1 plus 2 plus 3 plus 4 plus, and this goes on and on. So S1 is going to be 1. S2 is going to be 3. S4 is going to be 6. And then, S3 is 6. S4 is going to be 10. Now, if you think about Sn, this looks like Gauss's work, and we know that that will add up to n plus 1 divided by 2. And when we find the limit as n goes to infinity for this partial sum, you will get infinity, which is not a number. So we then know that this infinite series will be divergent. So the next infinite series that we're going to work with is a very specific one called the geometric series. Notice a couple of properties with this geometric series. In the first setup, k is equal to 0. When you substitute the 0 in, you get r to the 0 power. But this is equivalent to the series when k is equal to 1. So when you substitute in your 1, you're going to again have r to the 0 power. So these are essentially the same series. Now, take the time to write out 3 or 4 partial sums so that we can find S sub n. So first, did you recognize S1 is equal to A, S2 is A plus A times R, S3, and then we have Sn. We're going to do a little bit of algebra now. Take R multiplied by S sub n, you will have a times r plus ar squared plus ar cubed, and then that goes all the way to ar to the nth power, because when you multiply by r, the negative 1 will cancel out. Now we're going to combine these two terms, Sn minus r times Sn. Think about what's going to happen. We will have a, then ARs will cancel out, AR squareds will cancel out, AR cubes are going to cancel out, and even AR to the n minus 1 will cancel out. What will not cancel out will be A to the Rn, but we will have minus because that would be subtraction. Do a little bit of division now to factor out your S of n. We're left with 1 minus r, and we have a times 1 minus r to the nth power. S of n is then equal to a times 1 minus r to the n divided by 1 minus r. And there we have solved for Sn. So check out S of n. We do have a small problem. S of n may converge depending on the r value, but it may also be divergent. So we need to think about this problem based upon the r values. So next, let's go and see what happens if we let r equal 1. So if r is equal to 1, we can go back to S of n right here and say that S of n is going to be equal to a plus a plus a, and how many times is this going to happen? N times. So S of n is going to be equal to n multiplied by a. And if we take the limit as n goes to infinity of n times a, we know that answer is infinity. So wait, that means with r is 1, we have a divergent series. That's a bummer. But what if we let r equal negative 1? Let's try that. S of n is going to be equal to a minus a minus a minus a minus a. And how many times is that going to happen? Let's see here. This is going to be 0. And then we will have negative a. How many times? N minus 2 times. All right, so now the limit as n goes to infinity of negative a times n minus 2, your answer goes to negative infinity. So that's negative infinity. Again, if r is negative 1, our geometric series is divergent. What happens if we're between 0 and 1? We have the limit as n goes to infinity, a times 1 minus r to the n divided by 1 minus r. Now, as n goes to infinity, this expression is going to go to 0 because the r value is between 0 and 1. If that happens, our limit is going to be a over 1 minus r. Next, let's see what happens if r is bigger than 1. Let's take the limit as n goes to infinity, a times 1 minus r to the n of 1 minus r. So as n goes to infinity, this exponent is going to get to be giant, and we will have negative infinity as our possible answer. And that tells us that this part is divergent. All right, so now we put it all together. We have the series k equals 0 to infinity is equal to a divided by 1 minus r, where the absolute value of r is less than 1. If it's any other number that is not less than 1, then you have a divergent function, and it does not converge to a over 1 minus r. So now let's look at a few examples. We definitely have a geometric series, and our r value is equal to 2 over 5, which is less than 1. However, the index is starting at 0. When you substitute 0 into your exponent, you do not get 2/5 to the 0 power. We're going to have to do some special things. If we were to think about this, starting at k equals 0, do your substitution, you have 8 times 2/5 but k is 0 to the -1 power. So that's k equals 0. But remember what happens. We have all the rest of them to do from 1 to infinity of 8 times 2/5 times to the k minus 1. Now think about what happens next. If I were to actually substitute this 1 in for your k, I do get 2/5 to the 0 power. So my formula does work for the second part of the problem. Your a value is going to be 8, and then we're going to divide by 1 minus 2/5, because that's your 1 minus r, and we keep this original part of your problem, which is 20. So we have 20 plus 8 divided by 1 minus 2/5, which comes out to be a nice little 100/3. Alternatively, if you recognize that when k equals 0, you have your starting value as 20, then you could rewrite the whole problem as 20 divided by your 1 minus r, which is 2/5, and then you once again end up with 100/3. So it's a different way to do the same problem. Next, look at number 2. Again, did you notice that it starts at k equals 0, and that's not quite right. This problem will converge. Can you figure out to what? Go ahead, finish up questions 1, 2, 3, and 4. Next, we're going to discuss the nth term test. If your infinite series converges, then the limit of your nth term must be equal to 0. However, just because your limit as n goes to infinity of the nth term equals 0, it does not mean that your infinite series converges. Lastly, if the limit as n goes to infinity of your nth term does not equal 0, then your infinite series will diverge. So we can use the nth term test for a quick test to see which series definitely diverge. So if I take the limit as n goes to infinity of 2 to the nth power, that is going to infinity, which is not 0. Therefore, we know that this series diverges. For our next question, we're looking at a very special series. It's called your harmonic series. The way we recognize a harmonic series is it will be 2/k or 1/k, some sort of number divided by k, and that's a harmonic series. So if we take a look at the limit as n goes to infinity, 2/n, the answer to this is going to be equal to 0. So it could converge, but we don't really know with the information we have. But I'm going to let you in on a little secret. This one will diverge. It always diverges. It's called that harmonic series, and we're going to prove that it diverges later. Will our next problem converge or diverge? Take a look at it, rewrite it. Maybe it'll be recognizable if you think of it as 1/2 raised to the k minus 1 plus 1/3 raised to the k minus 1. Practice your nth term test. See what happens. The next one. We have some factorials in this problem. Let us understand what is happening. If we take the limit as n goes to infinity, they shouldn't be k values, n values. These are k's. So that we can substitute n factorial over 2n factorial plus 1. Think about factorials for a moment. This gives us the limit n goes to infinity, n times n minus 1 times n minus 2, and that goes on divided by 2 times n minus 1 times n minus 2. That one goes on and on. The plus 1. 1 is your lower order term. It gets dropped off. what happens? We cancel out our like factors. Don't forget n is also going to be canceled out because it started at n. You're going to be left with 1/2. Wait, 1/2 is not 0, so that tells us that our infinite series is going to be diverging. So it is divergent infinite series. Now, we've done so much today. Let's wrap it up. We know that a series converges if and only if its sequence of partial sums converge. We also know that your geometric series is going to converge if the absolute value of r is always less than 1. But if it's greater than or equal to 1, you will have a divergent series. If you have a convergent series, it will converge to the sum a over 1 minus r, and remember to think about your exponents as you use that little formula. For your harmonic series, so it's your special series, you have 1 over k, and that is always going to be divergent. I don't know if you remember, but when we did the integral from 1 to infinity of 1 over x dx, that was also divergent. No, that's not a coincidence. You have a divergence test now. If you take the limit as your n goes to infinity for your nth term of your series, and it does not equal 0, then we know that your infinite series will diverge. All right, so you now need to do a lot of practice. Have a great day.